Texan Global School. Combinations of functions. In this class, types of functions and combinations. A function is a correspondence between the elements of two sets that associates with each element of the first set, domain, a unique element of the second set, range. Let's remember from previous classes that every function is a relationship, but not every relationship is a function, as can be seen in the diagrams. Essentially, assign values to a function according to its domain, and by substituting, results values from the range or vice versa. In general terms, there are algebraic and transcendental functions. Algebraic ones are classified as polynomial, rational, and radical. And in the transcendental ones, there are the trigonometric, exponential, and logarithmic. These types of functions have already been discussed in previous classes. On the other hand, there are piecewise defined functions. They are functions defined by different formulas in different parts of their domains. For example, a function f is defined as x plus 1 if the domain includes all real numbers less than 1, and x squared if the other part of the domain includes values greater than or equal to 1. Let's evaluate in graph. To perform the evaluation, analyze the value of the given abscissa and the interval in which it falls. This will define the function in which it will be substituted to obtain the ordinate. Since f is 1, it indicates that x is equal to -1 and falls in the interval when x is less than 1. So by substituting x plus 1 into the function, results 0. For the second case, since f is 0, it indicates that x is equal to 0 and falls in the interval when x is less than 1. By substituting x plus 1 into the function, results 1. And since f of 1 indicates that x is equal to 1 and falls in the interval when x is greater than or equal to 1. By substituting x squared into the function, results 1. To sketch the graph, tabulate each function according to its domain. In the first function, x plus 1, propose values less than 1. Remember that the value of 1 must be included in the tabulation, and an empty circle is drawn as an open interval. Now, for the tabulation of the second function, x squared, propose values greater than or equal to 1. By graphing, we can see the behavior of the function, which begins as a line and jumps towards a section of a parabola. Another important concept in functions is symmetry. If a function f satisfies that, f of -x is equal to f of x for every real number x in its domain, then f is called an even function, because its graph is symmetrical with respect to the y-axis. We can see in this example that a parabola is symmetric with respect to the y-axis, since if we substitute x with -x, the function is not altered. It is also said that a function f is increasing over an interval I if f of x1 is less than f of x2, whenever x1 is less than x2 in the interval. Likewise, f is decreasing over an interval I if f of x1 is greater than f of x2, whenever x1 is greater than x2 in the interval. Using the same example, we can see that the function f of x equal to x squared is decreasing on the interval less than or equal to 0 and increasing on the interval greater than or equal to 0. Also, we can perform operations or combinations between functions. Literally, add, subtract, multiply, or divide the functions between them at the intersection of their domains. There is another operation called composition defined as f of g of x. Let's look at an example. We perform operations between functions if f of x is equal to the square root of x and g of x is equal to the square root of 1 minus x squared. Recalling previous analytical geometry classes, the domain of f of x includes all real numbers greater than or equal to 0. We can see that if we substitute negative numbers, results imaginary numbers. And the domain of g of x includes all real numbers greater than or equal to -1 and less than or equal to 1. Likewise, any value outside that domain will result in imaginary numbers. Now, the intersection between the domains includes all values between 0 and 1, including those endpoints. As we mentioned before, simply add, subtract, multiply, and divide the functions to perform the combinations on the interval obtained. But we must consider a change on the last operation. Since it is a quotient, the domain does not include 1, because the quotient would not exist because of the 0 in the denominator. In composition between functions, simply substitute one function inside the other and develop as you can see in both cases, thus obtaining new functions in each case, which graphed are shown on the blackboard. We see the initial functions f of x represented and g of x, as well as the functions resulting from combinations and composition. If f is a function whose ordered pairs are a, b, its inverse function is one in which the components of each ordered pair are exchanged as b, a. Let's look at an example. The inverse of the function y equals x squared, which, graphically, is a parabola. It is x equals y squared. Graphically, it is also a parabola but lying flat. We can see that the inverse is not a function, since if we draw parallel lines to the y-axis, they touch more than one point on the graph. We conclude then that the inverse of a function will not necessarily be a function, as in this case, it is a relation only. Finally, a function of the form y equals f of x is an explicit function, since the value of y, or dependent variable, is specified or isolated. On the other hand, an implicit function is one of the form f of x, y equal to 0, where the dependent variable is not specified or isolated. We can see in this example a series of functions. The first two are explicit functions, since the dependent variable y is isolated. The last two are implicit functions, since the dependent variable is not specified.
Texan Global School. Global online learning. Knowledge for the world. www.texanglobalschool.com